quantitative solubility in relation to a term that we're going to be looking at, not just in this video, but even the next video, of Ksp. Now, what are the similarities of these two terms? Well, the first one that we're looking at, this quantitative solubility, it's just the study of equilibrium. Now, we're obviously still in the equilibrium section of our series of videos, okay, in our kind of playlist, right? So it's the study of equilibrium position of saturated solutions. Now, this term here, saturated solution, is very important because it transitions nicely with this Ksp value that we want to talk about over here. Well, first of all, what do we use this Ksp value for? Okay, what do we use it for? This Ksp value, we use this because it is the product of maximum. Just put max here, okay, for maximum, okay? So for maximum amount that can remain in a solution. I'll just put in here in brackets dissolve, okay? And of course this all needs to be under a given temperature. So why did I talk about the saturated solution here being important? Because obviously saturation, okay, if a solution is saturated, there is a maximum amount that can remain in that solution. Anything more than that will start to precipitate outwards and is no longer going to be able to dissolve properly. So when we study this quantitative solubility, we need to know what our Ksp value is. If we don't know what it is, we need to be given another term, for example, molar solubilities of the compounds, like solids, for example, or other solubilities in maybe different measurements, like grams per liter or milligrams per liter, etc. We're going to have a look at a few examples of these anyway when we do our practice problems. I just want you to kind of be carried away with one concept, okay, that we use this Ksp in order to answer our questions when dealing with equilibrium positions of specific saturated solutions. So how can I conclude this? I can conclude this as, therefore, any two concentrations that, when created as a product, so now obviously you should know that when you create something as a product, you're going to be multiplying the two, right? So when we create something as a product and it exceeds that max amount, okay, of the saturated solution amount, so if we exceed that max amount, it will precipitate out of the solid. I want you to have a look at this example here, potassium hydroxide, okay? And this potassium hydroxide has a Ksp equaling 16. What does this mean? Well, just again, as a disclaimer, I want to put this all as moles per liter. And within these two categories, I'm going to be putting a cation on one side and an anion on the other side. So let's say this here is the cation. Let's say here is the anion. And of course, these are on concentration, so I could be putting these brackets around, okay, but I don't necessarily need to because I know that I already stated in the beginning that these are all in moles per liter, which is obviously concentration, but we'll just keep the brackets there anyway. So let's just start with maybe, let's say 1, okay? So if we have a concentration of 1 here, okay, and then this is 1 ion, okay, if it's going to multiply with this one over here, right, because when you create a product, you obviously have to be multiplying the two concentrations, okay, so when we have these two concentrations created as a product, when you multiply these two things, okay, so these two things here, If it has a Ksp of 16, it must add up to 16. If it's anything more than that, it's going to precipitate out of the solid. So in order for it to equal 16, what does this anion have to be here? Obviously 1 times what gives you 16? It's obviously 16, so we have to be putting a 16 over there. And what if I do a number 2 over here? Okay, so let's just multiply by 2 every single time as we go downwards. Okay, so it's an easy kind of trend to follow. So if we have number 2 over here, of course this value here, in order for this for the product result to be 16, would have to obviously be 8. Okay, so 2 times 8 gives you 16, so there we have that. And then if you keep going down, okay, so 2 times 2 gives you 4. Okay, so obviously in order to get a product of 16 using this 4 value, what do you have to multiply it with? Obviously another 4, so then we have 4 and 4. Okay, we can just keep going downwards as we go along. So obviously now we have 8. Okay, so we've got to do 8 times what gives you 16. Obviously it's just 2. And then of course, last but not least, if we do 8 times 2 gives you 16 over here. 16 times what gives you 16? This is also going to be 1. As you can see, this is kind of a flipped arrangement of this one over here, and this one here is flipped over there. Okay, so what does this mean? Okay, what are these values that I'm trying to tell you here? These are the possible ion concentrations that can pretty much only exist for the concentrations of this cation over here, this potassium, and the concentration of this anion, this hydroxide over here. So I'll just put here, these are the possible ion concentrations that can exist for this K plus concentration and for the concentration of the hydroxide over here. Which solid can have more mass dissociate in 1 liter of solution, this compound or this compound? I want you to know as a disclaimer right now that I have to give you the Ksp values. So you will likely also be given some Ksp values from your teacher as well. Okay, probably some sort of sheet that outlines different types of Ksp values for certain compounds. In this case, I'll be just giving you just for the AgCl and for the CuCl. For AgCl, the Ksp value is going to be 1.77 times 10 to the negative 10. Whereas CuCl over here is going to have a Ksp value of 1.72 times 10 to the negative 9. Based on what I talked about regarding the Ksp value, in case you kind of forgot what the Ksp value word for word definition was, the Ksp value, remember, was the product of concentrations, I'll just put here brackets for concentrations, of maximum amount that can remain in a solution. I'll just put here in short for solution. Okay, so they got to dissolve within it. And of course, these are all, as a disclaimer, at a given temperature. Okay, remember this maximum value over here has to do with a saturated solution. Okay, so which solid can have more mass dissociate so that it can have a higher saturated value amount and dissolve and be able to remain in that solution without any excess amount of precipitates forming out? Well, remember, Ksp is this definition over here, and based on what we've just talked about, it's quite easy to tell that a Ksp value of a smaller value would be less soluble, because what would it mean over here? The concentration that we can fit in there is lesser. If there's a lesser amount of concentration that we can remain, that can remain in the solution, obviously it's not going to be very soluble. However, if you have a product of these two concentrations and you can fit a lot of them and they can remain in the solution while also dissolving, of course this is going to be a very, very highly soluble solution. So I can just kind of put here that Ksp of smaller value equals less soluble. And of course, vice versa would also be true. Ksp of a greater value would therefore be more soluble. So, which one is a greater value? This value or this value? Obviously, this one here is going to be of greater value. So this here is the correct answer because obviously we can fit a lot more of this CuCl. It's a greater value. It can obviously dissolve more per liter. Determine the solubility product constant for this solid. Okay, remember Ksp is pretty much solubility product constant. So obviously we're just going to be looking for Ksp. So what is this Ksp? That's what we're trying to find. Okay, if that's the case, let's first break this up a little bit. So this Ni3 PO4 let's have a reversible reaction where it's going to be creating some products. Obviously, if this dissociates and breaks up, it's going to have these two anions and cations, right? So what's the first cation going to be? Well, obviously, we have Ni on this side, so we'll have to be putting an Ni on this side as well, so that it doesn't violate the law of conservation of mass. So this nickel over here, it's, as you can see, the 2 charge came from this Ni, right? It moved over here, so obviously the charge for the Ni is Ni2 plus. We have to add it with our phosphate over here. So obviously this 3 came from here, so of course this has to be PO4 3 minus. Okay, remember these are specific concentrations, right? Now obviously this is not balanced, so we're just going to quickly balance it out. So obviously we got to be putting a 3 here, and of course we're putting a 2 over here, so now we are balanced. Okay, so like always try to use a ICE table in order to make sure that whatever you do is going to be clear and that we don't miss out on any important variables as we go along in this section. Now in the beginning we don't have any initial concentrations as described in the question, unfortunately, so we just got to be putting a 0 for both the reactants and the products over here. Obviously we know that this here is going to be used up, right? So we're just going to be putting a negative. We don't know what value we can be putting as a variable over here. We're not given anything. The only thing we're given is this solubility, right, of 7.8 times 10 to the negative 5 grams per liter. So the only thing that we can be putting is an unknown variable, so we're just going to be putting x for simplicity, and then of course we have a plus 3x over there and a plus 2x over here. So if we just keep going downwards, obviously e just means IC added up, so we get negative x, then we got a 3x here and a 2x over here. Okay, how are we going to finish solving this question? Well, remember, Ksp is what? Ksp is the product concentrations of maximum amount that can remain in the solution. Okay, so the product of concentrations. Where are our concentration products? They're right over here. Okay, so we're going to be taking our concentrations of our Ni over here, and we know that it has a 2 plus charge, and we're going to be multiplying it with our other concentration, which is our phosphate. And if you multiply these, now we particularly have a product, which is awesome. What's important to note here, so that you don't ever forget this, is that after you write down your little equation here for both our anions and cations, okay, we have a product of these concentrations to equal our Ksp value. Whatever coefficient that you have in front, this gets moved as an exponent as a power. Okay, so if this was a 3 over here, 3 comes up here. Okay, if there's a coefficient in front of here, in this case it tends to be 2, that's also going to be labeled and identified as a power. Okay, so we have Ni to the 3 and a PO4 3 minus to the 2. So what are we going to be doing next? Well, our Ksp needs to equal whatever this is in here. Well, what's in here? It's obviously our 3x at the bottom, right? There, you see how they're in line over there, and then these are also in line. So this one matches with this one, and obviously this one matches with this one, right? So we could be putting our 3x over here, And for this PO4, we could be putting here our 2x in there as well, okay? And obviously it's going to be squared. Now, what is our x value though? Do we have an x value? Well, this is why it's important to look at the question, and when it says solubility of a particular compound, that means that is the x value. So x over here is going to be this value over there. So let's get this value, 7.8 times 10 to the negative 5 grams per liter of concentration. However, before we continue and finish off our question here, we don't like to be dealing ever with grams per liter, right? We always like to be dealing with moles in chemistry. So I'm just going to quickly change this into moles per liter, okay? So obviously, whenever you're in doubt, multiply by a fraction. We have, what do we want to get rid of? We obviously want to get rid of grams, right? We like liters, okay? But we just want to change the grams into the moles. So of course, we want to get rid of our grams over here, so we're just going to be putting a gram there diagonally so that they can cancel, okay? But what's going to be on the top of this G is going to be our mole, okay? Because on our periodic table, we have grams per mole for every single element, and if we add them up, we can have them for every single compound as well. So as long as you can find the molar mass, grams per mole, for nickel 2 phosphate, you can just add that value over here. So how heavy is it? You should have been able to find in your periodic table by adding 3 nickels and by getting 2 phosphates and getting 8 oxygens, you're adding them all up together. The molar mass ends up becoming 366.02. I'll just be putting a 2 over there. Okay, 366.02 grams per mole of this nickel 2 phosphate. That's how heavy it is. Okay, so now we can finally get rid of this gram and this gram over here. So let's just keep going down. What do you end up getting for your concentration? You end up getting this value here, 2.13103 times 10 to the negative 7 moles per liter. Okay, so now we have the units that is preferred for our chemistry calculations. We have our x, which is the solubility of that. So we're going to be just plugging this into here and plugging this into here. Okay, so in our little equation here, again, we can just be putting 3 times whatever our x was. So we can do 3 times, this is our x, to the power of 3 multiplied by our phosphate over here, again 2 times whatever that x was, so 2 times this 2.13103 times 10 to the negative 7. This also has to become squared, so what does our Ksp value end up becoming? I'm getting a value of 4.75 times 10 to the negative 32. This here is your Ksp value, your solubility product constant. As you can see, the Ksp has already been given to us. Okay, so the Ksp here is going to be 6.6 times 10 to the negative 6. Oh, dang. So now we got to find the x value, right? Because now it's asking for us to find the solubility of that particular solid. Okay, in this case, our compound is is lead to bromide. So first of all, they're asking for it to be in grams per liter. Let's just first do like how we always do in moles per liter, and then at the very end we can change it to grams per liter. So let's first write out our compound over here, reversible reaction, and used to create its anions and cations. So obviously we have Pb, okay, the 2 came from this Pb over there, so it's a Pb2 plus, and then our Br over here, it's going to be 1 minus. Okay, so now we have that. So I'm just going to be putting in our ice table because we obviously love our ice tables all the time. Okay, it never fails. Of course, for initial concentrations, nothing given in the question, so we can just be putting 0, and then of course it's going to be used up, negative x. These are obviously going to be added up, so it's going to be putting plus x, okay? But is there any coefficients in front of these x's? Well, obviously this is not really balanced properly, so we obviously got to balance it, so we're going to be putting a 2 over there, and we are good, okay? So obviously this is just 1x, and this becomes 2x. Now we're just going to be bringing these down, and now we're good. So remember, before you continue anything, you always have to remember, okay, remember what is the Ksp, okay? The Ksp again, it's the product of concentrations of maximum amount that can remain in a solution, okay, at a given temperature. So Ksp is going to be the product of these concentrations. What is our concentration? It's going to be this one. It's going to be this one over here. For our Pb, let's just put that concentration over here. And as you can see, there is only one coefficient, so I'm just putting a 1 over there. For our Br minus, okay, obviously there's a 1 minus charge, but there's a 2, so this has to be added up there as our exponent, so that becomes a 2 up over there. So as we continue to go downwards and we start plugging in our values, right, our x over here and then our 2x over here, we have to be making sure that we get our exponents included as well, which we've done. Okay, so our Pb here just becomes x, this becomes to the 1, and then this Br minus becomes a 2x, and of course this also needs to be squared. Okay, please remember that this needs to be involved with the multiplication of the 2, and this also goes with that x over here separately on its own before you start doing a product of multiplication with our x to the 1. So if this is our x to the 1, this here is obviously going to become 4, and then this becomes a squared. And then now we can finally multiply these two things together. So obviously 4 times 1 just gives you the 4 concentration here. Then this x to the squared and this x to the 1, the exponent rule, you just add this 2 with that 1 over there. So you just get 3, so you just get 4x to the 3. Okay, and of course our Ksp values just keeps going down here. In fact, that we actually have our Ksp value. What is our Ksp value? Our Ksp value was 6.6, right? So let's just write this in here as well. 6.6 times 10 to the negative 6. So let's bring this up here now. We've got to isolate obviously for our x in order to find our solubility of this particular compound. So you're just going to divide by 4. You do it on the right side, you got to do it on the left side. Okay, so this cancels out, this cancels out. What you end up getting, x to the 3 is equal to this. 1.65 times 10 to the negative 6. And then obviously we just need to be doing the cube root on the right side if we do it on the right side to isolate for our x, right? So these cancel, then you obviously got to do it on the left side over here as well. So our x becomes what value? 0.011817, and of course this is all in moles per liter. So is this what we want? Well, close, but we have to find it in grams per liter. So let's just quickly get this value that we got in moles per liter, and of course we have moles over here, grams on there, because obviously we want grams over liters. We don't want our moles. Okay, so obviously if this moles is here, we want to get rid of it. The only way to get rid of it using this factorial analysis is by having diagonally another mole on the bottom here, diagonally that they can cancel out. Okay, so just find the molar mass of our PbBr2. I'll give you a second to try that on your own. 367.01 grams per mole, okay, of that PbBr2. So let's just multiply these together. You get 4.34 grams per liter. That's your answer. So these are the two green questions of the day. This here's the first question, this here's the second question. Please pause the video, try this yourself on your own, and I'll be giving you the answer shortly. This is the answer to the first question. This is the answer to the second question.